Great. Hi, everyone. Welcome to session 3 of the statistics crash course, stats crash course. So today we'll be talking about ANOVA, analysis of variance. One way, as you can see on the screen, one way, two-way, factorial ANOVA, Driscoll-Wallace test, interaction effects, order effects, ANCOVA, and post hoc tests. So first of all, I guess the most basic ANOVA you could do is the one-way ANOVA. It's also known as an F test because it uses the F statistic. So just so we know, ANOVA stands for analysis of variance. And one of the common units of ANOVA, if you will, is, I like to think of it as sum of squares. Now, not everyone will agree with me, but I like to think of the basic unit of the ANOVA as sum of squares. Now, that's usually it just gets shortened. Usually it just gets shortened to SS and sum of squares, but sum of squares is still short for something else because sum of squares is by itself, it's kind of meaningless because it's sum of what squares. So sum of squares, but it's actually the sum of squared deviations from the mean. And I'll just explain that shortly. Sum of squared deviations from the mean. So if you just think about it, sum of the squared deviations from the mean. The squared deviations from the mean. What does that remind you of? Variance, right? Reminds you of variance, and absolutely it is totally about variance, because what does ANOVA stand for? Analysis of variance. So first of all, I want to introduce a concept called total sum of squares, and again I just have a number line sort of written up, and let's just have the same thing. I think we did this in seminar 1 or something. The mean of these 5 values was 3.8, and you can see from there. So you just get the subtractions from all of these from the mean. And so that's not enough. You need to do sum of the squared deviations from the mean. So in order to get total sum of squares, you need to get the total sum of the squared deviations from the mean. If I added all of this up, it would just be the total sum of squared deviations from the mean. Would that be variance? No, it would not be variance, because in order to get variance, you still need to divide that by 5 because there are n equals 5. So just be careful. Sum of SS, TSS, or SST, or whatever you want to call it, SS subscript T, that is ultimately the total sum of squares. And if you just have one variable which has the values 1, 2, 2, 5, 9, just this set of numbers, the total amount of variance is captured by this TSS figure. All right, so that's the total amount of variation there is. Now, in this equation thing, in order to get the F statistic, the concept of this, but that's wrong, so I'm going to correct that now. It's actually the sum of squared deviations between divided by df1, and then F equals sum of squared residuals divided by df2. So now you have 2 degrees of, you have 2 df's, df1 and df2. So in words, how would I explain a one-way ANOVA? I would say the F statistic is a ratio of the amount of variance. Oh, thank you, my bad. It's the amount of variance between groups divided by the amount of variance within groups. So just think about it, the amount of variance between groups divided by the amount of variance within groups. And does that remind you of something else that we've already covered? Yes, the T statistic, the T test. And so that's the connection, I guess, if you will. So in order to illustrate this graphically, let's say we've got placebo, drug X, and drug Y. Let's say we have a value here. Interesting. Okay, I won't touch that again. All right, let's say you have a value here, a value here, and then a value here. Now, with these three, if you have whatever's on the y-axis, doesn't really matter. If you get the grand mean, so let's say that's the grand mean of all values, and that's the grand mean. So if you were to calculate the F statistic, you'd have to calculate the deviation from the grand mean to the placebo group, the deviation from the drug X group to the grand mean, and the deviation from the mean of the drug Y group. And then if you did F equals, you add up those, square it, add up that, the middle one, it's a bit smaller, but then the third one's a little bit larger, square it, then divided that by the variation within the groups, so you can see if we did that squared, and then don't forget you have to divide that by df1 and then divide this by df2. Then you'll get a ratio. And if the ratio is roughly 3, let's just say it's roughly 3, then you can go look at the F probability distribution, and it will look like something like this. And then if F equals 3, F is on the x-axis, the probability of this will be 0.04. So if the p is 0.04, is that a statistically significant p-value? Yes, it is. So therefore, you declare a significant result. In essence, the one-way ANOVA, that's what it's there to test. It's there to test if there is a if there's a difference between any of these three groups. It tests the hypothesis of, it will test the hypothesis. I'm going to go to the next page soon. Whether the placebo group, group A, the mean of group A is different from the mean of group B, is different to the mean of group C. So in order to describe this, I might just wait a little bit. In order to describe this on the next page, the null hypothesis would therefore be, null hypothesis would be mu1 is equal to mu2 is equal to mu3. Alternative hypothesis, sorry, H1 it should be, so mu1 is not equal to mu2 is not equal to mu3. So those are the tests that it does. So I'll just go back down. That's what it was. And those are the hypothesis tests that it checks. Now, the ANOVA table is quite an important table to get your head around because, so you've got an ANOVA table, that's an example of an R output, and in the ANOVA table you get something called the F statistic, which we've already covered, and the p-value. Now, in this group, there are three groups down here in this example. Well, actually, in this example, we're just talking about the heights of groups A, B, and C, I think. In this example, it's a separate example. The between group sum of squares was 8,823.6, and there were three groups. So if there are three groups, if k equals 3, then you have 2 degrees of freedom. And therefore, you just go 8823.6 divided by 2 equals 4411.8. And then the remainder the remaining sum of squares is just allocated to something called residual. Now, sometimes it's called residual, sometimes it's called error, and this is slightly disjointed, I do apologize, but it's sometimes called residual sum of squares or error sum of squares, and it depends on the software that you use. I think in SPSS they call it error, and that's not great because error makes it seem like you did something wrong. No, that's not really right. Residuals, I prefer using that terminology. So the residuals, so the sum of squares illustrates that in this example, 8,823 is the between group variation, whereas the within group, within the remaining or the rest of the variation is has got 8,284.3 sum of squares. Now, because there were 30 people in this group, how do I know there were 30? Because 27 plus 2 is 29 degrees of freedom, and so there were 30 degrees of freedom. Sorry, there are 30 total people, but there were 29 degrees of freedom. 2 of them were allocated to the groups A, B, and C, whereas the remaining 27 residuals were allocated to residual. So 8,284.3 divided by 27 goes to 306.8. And then the mean square is just 4, and then to get the F value, you get 4411.8 divided by 306.8, and that will give you 14, a ratio of 14. And that ratio of 14.4 or 14.379 is a ratio of the amount of variance between the groups divided by the amount of variance within the groups. And that gives you a probability of something very small, 5.6 times 10 to the negative 5. So in other words, it's saying that if the null hypothesis was true, you'd only have 0.000056 chance of seeing the values that you see, or observing the values that you see. And so that's why it's statistically significant. It's lower than a 1 in 20 chance. Therefore, we declare, yes, there is, we reject the null hypothesis and accept the alternative hypothesis. Now, I should also add that ANOVA is, all of these are all extensions of something called the linear model. And with linear model, you may remember from, I think, maybe year 9 mathematics, something called y equals mx plus c, and something called, you may have done regression, but basically it's intercept and also the gradient. Now, that will go into in the actual regression lecture, but I will also add that you will also see all of these types of outputs from R as well. Now, I would just ignore all of these. That's just some summary stuff. However, essentially, you'll get coefficients. And so in group A, B, and C, you're going to have something that looks like this. So if I'm just interpreting these 163, 16, and negative 24, what this is meaning is that group A, group B, group C, this one was 163, group B was slightly higher at 163 plus around 17, so that's about 180, whereas group C was negative 24, lower, and so that is 163.3 minus 24.8, which is roughly 138. So yeah, that's how you would interpret that. And then there's the standard error. So standard error refers to this little bit. And then you get a t-value, 163.334 divided by 5.539 goes to 29.487. Now, what does this mean? 2e to the negative 16, that's a probability value that's very, very small, and a probability value of that small means it's highly significant. What that is saying is testing the null hypothesis that 163 is statistically different from 0. And it should come as no surprise that the value 163 is very statistically significantly different from the value 0. But you can also see, why do we care? So some of the outputs from R sometimes, just because it's your data, you know, depending on your data, sometimes it just doesn't make any sense to care about it. So yeah, it's cool, nice. But yeah, it's not that important. Now, the other thing is that, what about this? 16.9, what is this saying? It means group B is bigger than group A by 16.9. Now, if that was statistically, well, it is statistically significant at 0.03988. If this was statistically significant, what does that mean? That means this value, 16.9, is significantly greater than 0. That means this value is significantly greater than group A, right? And so that's possibly something of interest. And then group C is also significant. And then group C, okay, I'll put 2 hashes, 2 stars. So that's some of the output, just interpreting some of that output. So negative 24.8 is statistically significantly different from 0, meaning that group A is different from group C. Now, what about the rest of these? 17.52 residual standard error on 27 degrees of freedom, multiple R squared, adjusted R squared, F statistic. So just remember this F statistic, 14.38, that's the same value as this one, 14.379, on 2 over 27. Remember how I said there were 2 degrees of freedom, DF1 and DF2, and that's the same p-value. Now, a lot of these numbers match up just because this is a one-way ANOVA, and so it matches up nicely. When we get into more complex two-way ANOVA and factorial ANOVA, these numbers will likely no longer match up. But anyway, overall, if I was to say do an ANOVA, at its core, I would be saying do this part. Create an ANOVA table, and that's overall what I mean when I say do an ANOVA. This part is something else that's related, but not at its core. So methods. If you were to report this, you'd say we did a one-way ANOVA. A one-way ANOVA was conducted in R review 4.1. The results, the 3 groups reported significantly different heights. F2, 27 equals 14.4, P equals that. That's how you would report it. Now, typically speaking, you don't, when you have an ANOVA, a significant ANOVA of F equals 14.4, P equals that, very small number, you don't actually know where the difference is. You just know that groups A, B, and C are different from each other. So you need to do something called post hoc testing. If you have a significant main effect, then you have justification to proceed with a post hoc test. So what I'm saying here is if your total F value is not significant, if 14.4 is significant, so you do have justification to go ahead and do post hoc testing to compare between A, B, and C. However, if you didn't have a significant F value, then you shouldn't proceed to do post hoc testing. Also notice how we can't do every comparison. What if we wanted to do group B versus group C? Look at that. We only did A versus B and A versus C. Notice how we can't do B versus C. Well, we could just alter the code and just artificially do that. That's not good standard practice though. You should do something called post hoc testing. So yeah, just remember, you have 3 groups, K equals 3, so you have 2 degrees of freedom. So yeah, what if we wanted to do group B versus group C? The answer, use post hoc tests. Okay, what you could do is just use t-test with multiple comparison corrections. So what you could do is just simply run a t-test between A and B, B and C, and then A and C. Then you'll get 3 p-values, and then you can do, what is it called? You can do post hoc testing. You can do Bonferroni procedures and such like. I will just say, I absolutely do not think you should do that. You should do proper post hoc testing, which I will show you at the end of today's session. Yeah, cool. All right, we're going to move on. A Kruskal-Wallis test. Yes. So a Kruskal-Wallis test is just basically, can you see that? Okay. It's the non-parametric equivalent of a one-way ANOVA. It's the non-parametric equivalent of a one-way ANOVA. So just like, okay, I didn't actually say it, but the one-way ANOVA is like so the one-way ANOVA, if you had k equals 2 for the one-way ANOVA, if you had only 2 groups in a one-way ANOVA and you did that, you'd actually get an identical result to a t-test. They're actually identical tests. And similarly, if you did a Kruskal-Wallis test when k equals 2, meaning you only have 2 groups, like male versus female, and you did a Kruskal-Wallis test, it would be exactly the same as doing a Mann-Whitney test. So yeah, that's just the relationship. So the input for a Kruskal-Wallis test, dependent variable, continuous. Now, you don't need to assume normality or homoscedasticity. However, yeah, and then the independent variable is discrete 2 or more levels, sorry. And then that's just an example. R output, again, the 3 groups, height versus the 3 groups. And then you'll get a Kruskal-Wallis of 19.357, DF equals 2, p-value is that. And you can just describe it like that. Now, if you did have significant main effect, and again, you have to look at the significant main effect, then you have a justification to do post hoc tests. And if you were to do a post hoc test, then you just use Mann-Whitney with multiple comparison, with multiple correction, with protection. Mann-Whitney with multiple corrections. Multiple comparison corrections, I should probably say. Let's write that in, multiple comparison. So that's just in reference to the fact that last seminar, I talked about protection when you have multiple tests. So yeah, and again, we'll talk about that multiple comparisons correction at the end. Okay. So that's pretty straightforward. Kruskal-Wallis test is like a one-way ANOVA, but yeah, but a non-parametric version. Now we talk about the two-way ANOVA. Now in this example, we have independent variable 1, which is group A versus group B versus group C. And then we also have independent variable 2, I think is also just A, B, and C. So we have independent variable 1 and independent variable 2. And you can see the ANOVA table now looks like this, because you have k equals 3 in both IV1 and IV2, independent variable 1 and 2. So you have 2 degrees of freedom for both, because it's just 3 minus 1 equals 2. Now, this value, I believe, is the same as the previous one. Nope, okay, I used different data. Never mind. Okay, right. So, yeah, so anyway, you get a sum of squares of that much using a very similar method that I did before. And then you just, and there are 2 degrees of freedom. So the mean square is 8,205 divided by 2, which is 4,102.5. And then for IV2, you get 358 divided by 2 equals 179. But then how do you get the F value for IV1 and IV2? Well, you need to do 4,100, and so also I should probably add residuals is just all the remaining sum of squares. Now, with the remaining sum of squares, there was 6,995.4, and again, there were n equals 30, and so therefore the remaining degrees of freedom was 25, because you can think 25 plus 2 plus 2 equals 29, and so again, that's the total degrees, total n there was. Total degrees of freedom plus 1 equals n. So therefore, the residuals was 6,995.4 divided by 25 equals 279.8. So the residuals term is actually really important. The residuals term can be expressed as unexplained variation. And if you were to calculate the F value, you always need to use the residual term, because then you can do something like 4,102.5 divided by 279.8 equals the F value 14.66. Similarly, for IV2, you can do 179 divided by 279.8 equals 0.64. And so you can see there was only one independent variable that was statistically significant, which was IV1. So a two-way ANOVA, this could be something like drug group for IV1 and ethnicity for IV2. And it could be just that ethnicity didn't make a significant difference to the data, whereas the grouping of drug did. But if you did have IV2, and let's say it was ethnicity, and you included it in the model of data is dependent on IV1 and IV2, then you could say that after controlling for IV2, for ethnicity, for example, you had 3 ethnicities. After controlling for ethnicity, IV1 was statistically significant. So that's the wording that you can use, and you might have read that in your studies as well. Now, what about the linear model? So again, this, so it gets even more complicated when you have when it's a two-way ANOVA, because you've now got 2 independent variables to talk about. You have IV1B versus C. So I think all of these was just A, B, and C, A, B, and C. So IV1B, IV1C, IV2B, IV2C. And so you can imagine these are all additive. So let's say I belong to group B for independent variable 1, and I belong to group C for independent variable 2. So so now I can use this to predict my value. I would be 172.9563 minus 0.2857 minus 2.9768 if I was IV1B and IV2C. So that's how you interpret the results from that. And again, all of these p-values, they're all just saying if it's statistically significantly different from 0. So the only significance you see is IV1C, whereas the other ones are not statistically significant. And as I alluded to before, the F statistic now no longer matches up. For example, the F statistic is now 7.651 on 4/25. So the p-value. So this doesn't really add up to the ANOVA table, because when you have a more complex model, it does some funny things. I have a feeling that it's how it got that was by adding the sum of squares of all of IV1 and IV2 and then dividing it by 4, and then dividing that against the residuals. Anyway, so that's what you'd write for the methodology. You'd say methods, 2-way ANOVA was conducted in R version whatever, and then IV1 exhibited an effect on height at 2,25 equals 14.7, and IV2 did not appear to affect height. And then you give the F value and the P value. So don't forget to report the degrees of freedoms, the 2 values, you need 2 degrees of freedoms to define an F distribution, and then also say what the F was, and then say what the P value was. Now, again, if you have a significant main effect, only if you have a significant main effect, then you have justification to do the post hoc test. These are versions of post hoc tests, although not quite, kind of, they're actually contrasts, which I won't really go into. But yeah, to state specific differences between groups within IV1, you'll need to use post hoc tests. And again, see the end of the session where we'll talk about that. So that's a 2-way ANOVA. Now, what we're talking about 2-way ANOVA, I should also mention these are main effect ANOVAs. Now, why do I refer to main effect ANOVAs? Well, because the next part is talking about interaction effects. And interaction effects are quite complex, even more tricky. So main effects are typically independent and additive. And that's why previously I could say, if I was part of group B and part of group IV2C, I could say 172 minus 0.28 minus 2.97. I can just do that because that's an additive effect. However, in life, in biology, very rarely are things purely additive. So for example, the tastiness of waffles as a dependent variable could be individually increased with the addition of chocolate. Similarly, the tastiness of waffles might also be individually increased with the addition of bacon, egg, and cheese. However, if you added IV1 and IV2, you probably wouldn't expect them to cumulatively increase the tastiness of waffles. You could probably expect IV1 and IV2 to interact with each other, and obviously to cause an even tastier combination. No, I'm kidding, I'm not Joey from Friends. But my point is that often independent variables do actually interact with each other. Another example, mobility in Parkinson's disease patients. So they might be improved by taking Sinemet as independent variable 1. However, if a patient has very late stage severe Parkinson's disease, and that's IV2, this could interact with IV1 such that mobility is not improved despite taking Sinemet. So the biology behind that is if you continue taking Sinemet as a Parkinson's disease patient and you're a late stage Parkinson's disease patient, your substantia nigra is so deteriorated that taking L-DOPA does not actually boost the amount of mobility. So as a result, you actually have worse. And so that's an example of IV1 and IV2 interacting with each other. And that's a very common thing in biology, unfortunately, because it makes our lives even more complicated. So let's talk. So now I just wanted to even delve more deeply into interaction effects. So I'm going to split the remaining part into half. Sorry, I can't really zoom out, but just I'm going to split the remaining thing down, the space down here into half, and also, actually into quarters. So first of all, in the top half, I'm going to talk about no interaction effect. If there is no interaction effect, we can expect parallel lines. Right, so if we expect parallel lines from this, then, so for example, we're going to do this. We're going to say the dependent variable is dependent on A, B, C. Oh, sorry. Let's just write in a legend at the top. So in this example, we'll have IV1, independent variable 1, has 3 levels. A, B, C, A, B, and C, whereas IV2 has 2 levels, just blue and red. So,
C change.
Hello? Oh, there's someone here. Oh, okay. So yeah, so we're just gonna say that IV2 has 2 levels, blue and red. Okay, so similarly, degree of freedom, sorry, DV. So let's just draw this. So you can see in blue, we have the first group, and in red, we have the second group. So my question is this: is there a main effect of, and if I presented this graph, is there a main effect of independent variable 1? And is there a main effect of independent variable 2? So this graph is essentially plotting it's essentially plotting dependent variable is dependent on IV1 plus IV2. Now, first of all, these are parallel lines, and that indicates that there is no interaction effect. So if I was to just collapse across IV1 being A, B, and C, I just get the mean of the two groups, and mean of the two groups. So I get something like this. DV is dependent on A, B, and C only. And then I just average it out and just get a straight line. So what A, meaning all the people belonging to A is averaged into one group, all the people belonging to B is averaged into one group, and all the people belonging to group C is averaged to one group. Is there a main effect of independent variable 1 in this example? Yes or no? Have a think. And just think it in your head. And you're absolutely right. There is no main effect of independent variable 1, right? Now, the reason is because you can see as you change from group A to group B to group C, it gives the same dependent variable. However, if we're to do dv is dependent on blue versus red, if I averaged all the red values, it would be like this. And if I averaged all the blue values, it would be like this. Is there a main effect of independent variable 2? Yes, because blue is different from red. And you can see that here as well. Blue is higher and red is lower. So there is a significant effect when comparing an independent variable 2. So IV2 would be significant according to the ANOVA table, and IV1 would not be significant. Okay, now let's do another example. If I had DV and I had A, B, C. Now if I did this, if your data looked like this, and your data looked like this, just based on this, would there be a main effect of independent variable 1, of IV1? Would this have a main effect of IV1? And let me just rejig your memory. What I would do is I'd first average all of A, and then average all of B, and then average all of C. Is there a main effect of IV1? Well, let's draw it out. And then average A, average B, average C, and then you'd get something that looks like this, right? Because we're averaging all of A, all of B, all of C. Is IV1 is it horizontal? No, it's not horizontal. There is a trend. And if it's not horizontal and there is a trend, therefore it is absolutely significant. So there is a main effect of IV1. Now, what about IV2? I should probably also add, this is IV1, this is IV2, and IV2 was significant over here. IV1 was significant in this case. And now, what about IV2? Is IV2 significant? Blue, red. In this second example, is IV2 significant? If you averaged all of these three versus all of these three, what do you get? Well, the red group seems to be a bit lower, whereas the blue group seems to be a little bit higher. So you also get significance in IV2. However, the only post hoc, so yeah, if you had significance, but the problem with this is that the only comparisons you could do, the post hoc comparisons you could do, and I'm going to write this in a little bubble down here, in a very tiny sliver of a bubble, my apologies, possible post hoc tests would be A versus B versus C, and also blue versus red. Blue versus red. So you can only compare between all of A versus all of B versus all of C, or you can only compare all of blue versus all of red. Do you see how you couldn't actually do this comparison? You couldn't actually do a post hoc test of this group compared with this group. You can't actually do that comparison, right? And that's why you also, if you wanted to do that comparison, then you should add an interaction effect. Because what did I say before? You can only do post hoc tests if you have a significant F value. And in order to have that significant F value, if you want to do this comparison, specifically the blue group of the A group versus the red group of the A group, if you wanted to do that, then you need to include interaction effects. And this is where I talk about interaction effects. Interaction effects And a significant interaction effect, if there were, or for example, if there was an interaction effect, then this is characterized by intersecting lines. So the most obvious example, the most like prototypical example of this would be something that looks like this: DV, A, B, C, the blue group versus the red group. So you have intersecting lines if it crosses like this. So now in this model, you could include the main effect of IV1, main effect of IV2, and the interaction effect of IV1 against IV2. And what you'd get is something that looks like this. IV1 would look like this: DV, A, B, C. Now, if I was to average all of A versus all of B versus all of C, would there be a main effect of IV1? No, because it would be all just horizontal. So that's not significant. What about IV2? If I averaged all the blue and then all the red, what would I get? I'd get something that looks like this. If you imagine if I averaged all the blue and the red values, it'd look like that. And again, there's no difference in IV2, so therefore no significance. However, if I did IV1 interaction IV2, and we use an asterisk sometimes or a cross to denote that, essentially you're now saying, no, I want to subdivide. So the blue group A, the blue group B, the blue group C, the red group A, the red group B, the red group C, and then I'll just this compared with this, compared with this, this compared with this, compared with this. Is there going to be an effect of this interaction term? Are these values all the same? Are all of these 6 groups all the same? Obviously no. So therefore, this will be a significant effect, significant interaction effect. And to get an intuition of that significant interaction effect, you can simply just look at that summary graph and see how there are intersecting lines. That's the first example I'll give for an interaction effect. The next example I'll give will look something like this. So again, IV1, A, B, C, and degree DV, dependent variable. So let's say the blue group looked like this, whereas the red group looked like this. What you'd get in IV1, if you were to collapse across IV1, yeah, what would you get? DV1, you get A, B, and C. You'd actually still get a trend, even though the red group would just sort of dull that trend. But you still get something that's slightly decreasing. Something that's still slightly decreasing. So this would still be significant. What about IV2? And then you'd have the blue group versus the red group. Well, you'd probably get something that looks like this, because again, you can see how there isn't, you'd have this sort of thing, because the blue ones are slightly higher than the red ones. So IV2, is IV2 significant? Yes, probably a little bit. Now, would there be an interaction effect, do you guys think? Well, let's draw it out. Sorry, it's getting a bit cramped. A, B, C versus A, B, C. So again, the red A, B, C's were all constant. However, the blue A, B, C's were decreasing. So are all of these values in this mini graph, are all of them the same? Absolutely not. So therefore, it would still probably yield a significant interaction effect. So this would be an example where all three, IV1, IV2, and the interaction effect are all significant. So it's just getting a handle on what interaction effects are and talk about. Now, if we were to do a post hoc test, possible post hoc tests or post hoc comparisons, you would be able to compare between all of the subgroups more effectively. Group A, B, and C, and then blue and red, and you'd be able to do all, different comparisons between all of them. Oh, you can't see that, sorry. You'd be able to do all the comparisons. So you can literally do like this one versus these, you can compare between these two groups, for example. So yeah, this is an example of the interaction effects. And interaction effects, you can just think, will these two lines intersect? Well, in this graph, it doesn't look like they do intersect, but if you continued on, they would intersect. So therefore, there would be an interaction effect. So it's just building intuition surrounding, looking at data. Cool. Okay. All right. So now that we've talked about what interaction effects are, how do you test for interaction effects? Well, you can use a factorial ANOVA. And so, for example, IV1 could have been sex, male or female, and IV2 could be race, and we have three races here, orcs, dwarves, and elves. However, there's a hidden detail. Males in general are 10 centimeters taller than females, regardless of race. So that's a main effect of sex. And then the other detail is that there's an interaction between sex and race. Maybe it just so happens that 80% of orcs are male, 50% of dwarves are male, and elves are mostly female. That's a hidden detail that you wouldn't have spotted unless you'd actually done an interaction term as well. So input of a factorial ANOVA, typical, dependent variable, you assume normality and homoscedasticity as usual. You have independent variables and they can be discrete typically. And an ANOVA table you'd get, so I printed two ANOVA tables. One of them was if you only did the main effects only, you'd have this. This is a two-way main effects only. These are the values you'd get. However, if you also included the interaction term, that's what you'd get. Now, you'll note that it doesn't actually become statistically significant. That's probably just because we have low numbers, but yeah, that's okay. But yeah, how would you run a factorial ANOVA? You just simply go height is dependent on race times sex, and you just have the main effects of race, main effect of sex, and then the interaction effect of race interact sex, and it uses colon to denote the interaction term. And yeah, that's the reporting you do. Race methods. A two-way factorial analysis of variance was conducted in R. Results: race appeared to exhibit an effect. Race appeared to exhibit an effect on height. F2,24 equals 83.5, and sex also appeared to exhibit an effect on height. F1,24 equals 4.3. However, the interaction term did not appear significant. So it's only if you have a significant effect that then you have the justification to proceed with a post hoc test. So because only the sex and only the height was significant, then you can do post hoc testing for height and sex, but you should probably not do a post hoc test for the interaction term, meaning you shouldn't do comparing male dwarves versus female elves. You shouldn't be able to do that because it's not, because that's part of the interaction term. You're subsetting within the groups. But yeah. But you can see how it wasn't, the P was 0.27, so you shouldn't do it. But if it was significant, then with a significant interaction effect, then you can test the subgroups within each sex and race combo to see which groups have higher or lower heights. So, yeah. Okay, let's move on. ANCOVA, analysis of covariance. Oh goodness, it's already 3:54. Okay, sorry, I should speed up. Okay, ANCOVA, analysis of covariance. So you have input, again, a continuous variable such as systolic blood pressure. Your independent variable should be, IV1 should be a discrete variable, and IV2 should be a continuous variable such as height. Now, suppose that height positively affects systolic blood pressure. So the taller you are, let's just say the higher systolic blood pressure you have, because you need to pump blood to a higher level and whatever, that is, taller people tend to have higher systolic blood pressures. We know this. However, we want to statistically account for this effect. We want to be able to see whether the drug or placebo affects systolic blood pressure, regardless of the effect of height on systolic blood pressure. So essentially, all I'm saying is, in order to draw a graph that looks like this, in order to be able to draw a graph that looks like this, you need to do an ANCOVA. Because if you didn't account for the height and such like, then you wouldn't be able to typically do that. Oh, I should probably put the x-axis as height. That's the point of a ANCOVA, to account for a continuous variable such as height when you want to look at like systolic blood pressure, for example. And you can see that's output from R. So again, you have an ANOVA table from here. The effect of height has a sum of squares, then you have mean sum of squares, and then a probability, which is the p-value. And then you have a drug sum of squares. And because the drug only has two groups, so therefore there's only 1 degree of freedom. And so that's the p-value. You can see they're both statistically significant. So you can say by methods by modeling systolic blood pressure against drug treatment along with height as a covariate, an analysis of covariance was done in R, and the results, by controlling for the effects of height on blood pressure via an analysis of covariance, or ANCOVA, the drug appeared to increase systolic blood pressure. So it's all about analyzing the covariates and making sure they're controlled. And again, only if you have a significant main effect, then you have justification to proceed with a post hoc test. Now, when you run your experiments, a lot of these data all basically assume that you only record one value from your participants, they only assume that you collect one data point from one person, which is just not true. You usually collect multiple data points from the same person or from the same animal. If you did rats, if you ran experiments on rats, then you might expose them to multiple different conditions. But the problem with that multiple different conditions is that they may have learning effects or carryover effects or washover effects. And that's a very big problem. So suppose you repeatedly expose a test subject or a participant to a treatment. You may be worried about the order effect. Suppose you're exposing each participant or subject to 5 conditions. So you need to be able to control for that. And so the most obvious one you could do is just full counterbalancing. So let's just say you had 5 conditions, or you had K conditions. If you had K conditions, you'd need to counterbalance using K factorial. Now factorial, so if you had 2 groups, if K was 2, then 2 factorial would just be 2. 2 times 1 is 2, and that would just be exposure A times exposure, followed by exposure B, and exposure B followed by exposure A. What does that mean? If you had 2 conditions, then you could have just 2 groups. This is just like the most typical crossover study. Person number one will go through the A experience first, followed by the B. Let's say A is drug and B is placebo. Then another person would go through B, followed by A. So that's a very typical placebo-controlled drug design study, whatever. But what if you had three groups? Let's say you wanted to test a placebo versus a low dose versus a high dose. Then how many different ways are there to do this? Well, there are 3 factorial. What does that mean? 3 times 2. Factorial just means 3 times 2 times 1. You just times it by sequentially lower numbers. So if you had 3 groups, then you'd have to expose to A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. So you'd have 6 possible orders. And that is problematic because then that means the minimum number of people you could recruit is 6 people in order to get that full counterbalancing. And what full counterbalancing means that you have every possible order in which people could do things. So if you had 3 conditions, that's 6 minimum. So you can only do groups of 6. So you could enroll 6 participants, 12 participants, 18 participants, 24, 30, and such like. But if you had 4 groups, then you need to do 4 factorial, which is 24. If you had 5 groups, you have to do 5 factorial, which is 120. If you had 6 groups, you would have 6 factorial, which is 720. So that means if you had 4 groups, you'd need to enroll 24 participants, 48 participants, I think, 72 participants, and it gets, or 96 participants, and so on. If you had 5 groups, you have to enroll in groups of 120, 240, because then you have to account for every possible comparison. And you can see that's way too much. Like, that's just not really possible. So the pros of this is every possible ordering of condition is expressed, and that's the best thing. I don't know why I wrote best there, but that's amazing because you can do every possible order, and then you can be very confident that after accounting for order effects, there is absolutely no way this is due to order effects because you've done every possible comparison. But the con is a lot of N is needed, and that's not good. So a way you could account for that is using something called a Latin square. And a Latin square, now let's just say, for example, K equals 5. Let's say you had 5 groups. Let's say you had placebo versus, and then 4 different concentrations of the drug. So what you could do is simply do, the person number 1 will go through, group 1 will go through 1, 2, 3, 4, 5. Group 2 will go through, and you just go 2, 3, 4, 5, 1. Group 3 will go through 3, 4, 5, 1, 2. Group 4 will go through 4, 5, 1, 2, 3. And then the 5th group will go through 5, 1, 2, 3, 4. So why is that? So how much N do you need? How much total N do you need? So if you had 5 conditions, like I said, 4 different doses and a placebo, and you wanted people to go through all 5 conditions, you need multiples of 5. You can have 5 people and have that sort of thing, and then you could have 10 people, so 2 in each order. You can have 2 people go through the first experience, 2 people go through the second experience, 2 people go through the third experience, 2 people go through the fourth. Or yeah, so you'll see that you'll have the total N needed will be multiples of K. So that, and as opposed to needing multiples of 120, you only need multiples of 5, which is a much more manageable N. So the pros of this is less N is, oh, sorry, you can't even see what I'm pointing to. The pros of this is less N is needed, but the con is not every level follows another level an equal number of times. And so there's still potentially a carryover effect. For example, let's just say group 5 was the placebo and group 1 was the highest dose of the drug. You can see the placebo follows group 1, the condition 5 follows group 1 once. However, group 5 never follows, is always before group 1 again. 5 is before group 1. So maybe every other condition does nothing except one condition. For example, let's just say group 5 is the one that actually does an effect, whereas all the other groups do nothing. And let's just focus on 1, for example. So Group 5 will have an effect, and it might have a washover effect to group 1 here, washover effect, washover effect, washover effect. So for 4 of these orders, there will be an effect because there will be a washover effect of group 5, but in only one of the groups, there won't be a washover effect because the 5th condition is after the 1st condition. So that's a problem in experimental design because you haven't actually properly randomized that. You want every condition, you want every level to follow every other level an even number of times to fully account for that. And so that's what the balanced Latin square design is. So for example, again, e.g. k is 5, let's say you have 5k, so you do, so condition 1 would just be 1, 2, and 5 in, that should be k, but 1, 2, 5, 3, 4, and then just add 1 to the next one, 2, 3, and because there's only 5, so you plus 1 is 6, but because there aren't 6 groups, is 1, so you do that. 4, 5, 3, 4, 2, 5, 1, 4, 5, 3, 1, 2, 5, 1, 4, 2, 3. However, if it is an odd number, because k being 5 is an odd number, you have to reverse it. And so what does that mean? You reverse it 4, 3, 5, 2, 1. 4, 3, 5, 2, 1, and then add 1, 5, 4, and then plus 1, 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 1, 3, 5, 4, 3, 2, 4, 1, 5. So in this example, you would need, if you had 5 conditions, if you had 5 conditions, you would need at minimum 10 n. You need at minimum 10 subjects, 10 rats, 10 people, or whatever, to fulfill the balanced Latin square. So let's count the number of times condition 5 follows 1. This is 1 time. This is another time. No, 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 yes, yes. So it exactly follows it, I think, 5 times, is it? 1, 2, 3, 4, 5. You can see condition 5 is after condition 1 exactly 5 times. And you can do that comparison with all of the other numbers, and you'll see that every condition follows each other condition the exact same number of times as it precedes the condition. So if you had an odd number of conditions, in this case k equals 5, so 5 is odd, then you'd need 2 times that. So the minimum number you would have is 10 to fulfill all 10 different 10 different orders. However, if you had 6, if k equals 6, I'll just write an example of that here. 1, 2, 6, 3, 5, 4. And then I'll just add 2, 3, 1, 4, 6, 5, 3, 4, 2, 5, 1, 6, 4, 5, 3, 6, 2, 1, 5, 6, 4, 1, 3, 2, 6, 1, plus 1, plus 1, plus 1. So what I'm trying to illustrate here is if you had an even number of conditions, like k equals 6, then you simply only need 6n or 12n or multiples of 6. So yeah, so you don't need to times it by 2 because then this is the Latin square. And that's what I'm trying to illustrate. I hope that makes sense. 1, 2, n, 3, n minus 1, 4, n minus 2. So it's just, yeah, I hope that sort of makes sense. So the total number needed, if you had even numbers of conditions, then you just need multiples of k, which is good. If you had odd, oh sorry, you can't see the numbers. If you had odd conditions, then you had 2 times the multiples of k. And the good thing about this is that there's less n is needed, but the con is that wait, no, that's a pro. Okay, that's a good thing. Every level follows another level an equal number of times. The con is probably that you still need quite a few conditions, but anyway. Yeah, so if you're trying to design an experiment which is fully counterbalanced and fully randomized for order, then that's a way you could do it using a balanced Latin square. All right, lastly, let's look at post hoc tests as I described. So, similar to last week's session, you need to account for multiple comparisons because numerous individual comparisons will compound type 1 error. You should only proceed with post hoc tests after a significant full ANOVA or ANCOVA or whatever model you use. It is possible to get significant post hoc tests, but still get non-significant ANOVA, ANCOVA main results. Note that the ANOVA or the ANCOVA model keeps family-wise error rate at 5%. You may have seen the words family-wise error rate. You always want to keep the family-wise error rate at 5%, which is the truth, like the overall aggregate, and that's what the ANOVA table does. It keeps it at 5%. But yeah, so one way you could do it is Bonferroni. So you first calculate the total number of comparisons possible. So for example, when I was doing this one, there are 6 groups, right? There was a blue A, blue B, blue C, red A, red B, red C. So you'd calculate the total number of comparisons. That's actually not true. You'd actually times 5 times, actually, I'll just write that down. You would actually do K times K minus 1 divided by 2. So if K equals 5, therefore number of comparisons would therefore, comps would therefore equal 5 times 4 divided by 2. 5 times 4 divided by 2, I think is 10. Yeah, 5 times 4 is 20. Divided by 2 is 10. So there'd be 10 different comparisons. And then you'd correct the individual comparisons by multiplying the p-value by the above value, which is 10. So if the p-value goes above 1, then cap it at 1. So if your p-value was 0.5, how would you correct it? You just multiply it by 10. So what's 0.5 times 10? It's 5. But obviously you can't have a p-value of 5, you just cap it at 1. Alternatively, you could divide the p-value by the threshold. So the p-value threshold, instead of being 0.05, it would just be 0.005. But yeah, however, the Bonferroni procedure overcompensates for type 1 error and makes it difficult to find significant results. And so that's a problem. And so that's why you might want to use a different type, like home Bonferroni. So this is just, I put that there, adjusted p-value equals 0.05 divided by then K minus rank plus 1. It's slightly less harsh than Bonferroni. So all these different names, Bonferroni, Fisher's, Tukey's, false discovery rate, they're just different ways to correct for it. Pick one of your favorite and use it. Just know that there are different ways to correct between them. Now, I guess the main thing is, my main question is, what is the difference between post hoc tests and multiple t-tests plus adjusted p-values? All right, so what do I mean? If I was to do a test, let's say I had this graph over here. I focused on this graph. If I just did a t-test between these two groups versus doing a full ANOVA, a factorial ANOVA followed by post hoc tests, comparing the blue A versus the red A, what is actually the difference? The t-test will only actually include that group minus that group, then divided by the within. It would only account for the data over here. However, if I did a post hoc test including the main effects of IV1, main effects of IV2, and the interaction effects, I'd actually be you know how there's the concept that I've been trying to get at was the value of significance, the T ratio or the F ratio is the difference between the groups divided by difference within the groups. That's what I've been trying to get at. If I did a post hoc test, that denominator would actually be the model residual. What do I mean? The model residual, it would be this value down here, 95.4 or 92.8. And why is that useful? Because that actually improves your statistical power because it's all divided by the noise of the model, of the overall model. So when the conceptual difference of doing just a t-test of these two values versus a post hoc test is that the post hoc test will actually use the residual of the entire error of the model as the denominator. And that's much more statistically powerful because you've taken into account the overall variation of the model. And so you're effectively using the variation of the entire set of data rather than just using, if you did a t-test, you'd only use the data from these two. So therefore, in a way, it's by increasing your N, if you will, by doing a post hoc test. So that's why I strongly would recommend doing post hoc tests rather than doing multiple t-tests, because multiple t-tests don't exactly account for all the data. It only accounts for the data within the two groups you're measuring, whereas the post hoc test accounts for the variation across all the numbers that you have in your model. So, yeah. Okay. Now is the time for the exercises. Okay. Right. So, as usual, I will now switch on over to my laptop and try to stop sharing. Okay. What am I doing? Okay. So now I'm going to swap to my laptop and get started on the exercises. I will talk through the exercise. Oh, right. No, you guys can't see this in person, so I need to switch to lecture and computer. And now I need to share my screen. Share screen. And then the people will be able to hide video panel. And then hide floating meeting controls. Okay, so great. Cool, awesome, fantastic. People on Zoom and people in person can now see my R screen. Okay, we'll go straight into it. Okay, Seminar 3. I've already preloaded up Seminar 3, the Stats Crash Course Seminar 3. So I'm reading from my notes here, not my notes, just the course manual. Imagine you recruit 200 blargs, a fictional alien species. You assign randomly each blarg to receive a drug X at 5 different doses, 0, 1, 5, 10, 20 milligrams per kilogram, where 0 milligrams means the blarg received a placebo. You then measure their strength level after drug administration. Strength is measured in arbitrary units from 0 to 100. Okay, so first of all, I think in my script, I always run libraries first. Running libraries first just says, okay, do I have all the libraries and all the commands that I'll use? Great, cool. Now, first of all, you need to set your working directory. So for those using Mac OS, you can always use, I think it's X and then users and then your username and then whatever that is, and then go to desktop or wherever you've put your data. For me, as usual, I'm going to go to this, and this is my set working directory, and except R prefers // and then I run that, and now my working directory is in the right place. And now I would like to, in my working directory, I'd like to load in df1 blarg. All right, so df1 equals read.csv seminar, oh gosh, I forgot what it's called. It's seminar3 underscore df1 underscore blarg. And then I think I call it .csv. And I think that's it. If it's not, then I'll know, and it'll punch out an error. And then I'll realize if it's gone wrong. Okay, cool. So you can see I recruited 200 blargs. If you're wondering why I called it blag, it's my feeling about my PhD. So you've got 200 blags and you have them all in different doses, 0, 1, 5, 10, and 20, and you've got their strength. Great. So now, first of all, as you always do structure, always view the structure. That's good practice. You can see ID is an integer value and dose is an integer. Now, I would prefer to make it all into a factor variable. So I'll run that as a factor variable. Then I'll run this, and also dose. I know it's actually, the dose is actually a continuous number, but because I've artificially grouped them into groups, I'm going to statistically treat it as a discrete variable, or into a factor variable. And so let's just view structure again. Great, they're now read as factors, and then I'll view the first 5. Great, that's great. You can always view it again, and you can be like, oh, cool, I viewed it. It's always good practice to look at your data. So I think in question exercise 3.1 and then number 1, I say roughly visualize the data to get an idea of the mean and variance. So you can simply say, well, the dependent variable is strength, and I want to visualize it against ID. Well, excuse me, how many people do you have here? Well, you have 200 blags. If you were to visualize that, then you have 200 blags and their strength is visualized like that. That's not particularly informative. Instead, let's group it by dose. That's probably more informative. And then if you just plot it like that, it will automatically, by default, plot a box plot, which is what you see on screen. Cool. Alternatively, you can also do a ggplot. Ggplot, that's the code for a very quick ggplot, and that's what will pop up. Cool, that seems cool. So you can kind of see, if you like really squint your eyes, that like group 5 might have a slightly lower dose. The strength of the people who received the 5 dose might be a little bit lower than the other doses, but I don't know. Now let's just run a one-way ANOVA, right? So this is the code to run a one-way ANOVA. Strength against Question 2, conceptual point. What happens if you perform a one-way ANOVA, strength against ID, see the R script? Let's just run this. Look at this. This is a conceptual point. If you run an ANOVA, analysis of variance against ID, how many individuals do we have? 200. And so if we run an ANOVA and say, well, we now have 200 individuals, so we have 200 individual groups, each person with their own groups. Do you see how R spits out an error saying, well, there is no more residuals, right? Now, the value of the sum of squared is 84409, and the mean square is 424.17. If I just calculate the variance of DF1's strength, it happens to be 424.1672. These are the same, well, they're rounding error, but they are the same numbers. Essentially, what I just did was I just calculated variance of that, because if I ran an ANOVA of the strength against every individual person by bucketing them into 200 individual groups, that's gotten me nowhere. That's just calculated the variance, right? So this is just a conceptual point. Hopefully that makes sense, because what you've done is you've overfit the data, and by overfitting the data, by overfitting the data, it's become the data's just become not meaningful, or the analysis has been not meaningful. Now, conceptual point, is dose a discrete or continuous variable? Well, as I told you before, as I alluded to, there are 5 different doses: 0, 1, 5, 10, 20. Now, that's actually, dose, of course, is a continuous variable, right? You can give any dose you want. However, my point in this is, okay, DF1 discrete. Let's just go through the code. So I've just called DF1 discrete this. If you look at this graph that I've just made, if I've treated dose as a discrete variable, what happens? Well, do you notice how the X value is equally aligned, is equally spaced, sorry? But now if I treat the dose as a continuous variable, if you look over here, now they're no longer equidistant, they're now at their original numbers, right? So it's just something to think about. If you treat a variable as discrete or continuous, it will also affect how you plot the data as well. So it's just something to keep in the back of your mind. Yeah. So for statistical analysis, you probably, if you want to do an ANOVA, you'd want to code it as a discrete variable. But for plotting purposes, you don't need to. Like, it's just how you want to view the data, but you might want to code it as a numerical variable instead. So that's just another conceptual point about the practicalities of coding in R. Number 4, perform a one-way ANOVA on the data. So this is how you do it. Name the model. So model 1 equals a linear model, LM, strength against dose, and then you perform an ANOVA of that, and then the summary. So that's, you can use summary, and then it prints out this linear model thing that I've shown you in the thing, but this is the ANOVA. This is the ANOVA from combining the 5 different groups and then measuring their, well, doing a one-way ANOVA on the data, right? Is that a significant effect? Significant main effect? 0.07 is the p-value? No, it is not statistically significant. Okay. Now, regardless of the results of this, let's just do a pairwise t-test with no correction. So you can do a pairwise t-test using this, and you can see how I did no correction. p.adjust.method equals none, so no comparisons. And then you have the different groups compared against each other. Now, what do you see? Are there any significant values in this group? Yes, there is. There's one. This one's also very close to significance, but it's not. It's just over the significance threshold. So does that make sense, right? So what am I trying to get at here? My point is, do you see how even though the ANOVA is not significant, if you, despite the F value, went ahead and did post hoc testing, you could still find significance? And for example here, if you compared group 20, the group of 20 and the group of 5, meaning this group, the group of 5 versus the group of 20, you'll find a significant effect if you did a p-value, if you did a t-test. However, you didn't have main effect significance, and you should always have main effect significance before you proceed to do post hoc testing. That's what you should, that's good science, right? And you can hide this so easily in papers. You don't even need, like, that's why you should always report your F value significance followed by post hoc test significance. But people can really cheat the system and game the system, which is really unfortunate. Okay, and the next one I think I say is to do post hoc tests. Now, in order to do post hoc tests, you need to install library em_means, and then so model 1 is this model over here where I did strength against dose, and then you just use em_means and pairwise against dose. That's just the script, the type of script you'd use, and then that now every possible combination, so 0 against 1, 0 against 5, 0 against 10, then you can look at all the p-values. Again, you still see one significance one, so even, do you see how the p-value is not exactly the same, 0.0425 versus the one when I did the t-test, 0.0054. They're not the same because they're different tests. A post hoc test and a post hoc test and a 2-sample t-test are different tests. However, again, even if you do post hoc testing, even if you tried to do some form of protection, you see in this one, they did the Tukey method for comparing a family of 5 estimates. Tukey is a very popular adjustment method. It still is statistically significant, right? So just be careful of that. You should always have a main effect significance followed by post hoc testing. You should not do post hoc testing followed by main effect. That's the wrong way around. Okay. Now, number 8, I think I asked you to perform a Kruskal-Wallis test. And a Kruskal-Wallis test, again, just one line of code, and it's very simple, done. The Kruskal-Wallis test is statistically significant, surprisingly, 0.04652. And regardless of the results from this, perform a pairwise Wilcox test. And again, R just has a natural, has a function for that. So just do that. Okay, so there are a lot of ties in the data, so that's why R printed out all of these warning messages. But nonetheless, you can look at this table. Are there any significant things? Yes. Group 1 against 20 was significant. Group 5 against 20 was significant. So 1 against 20 was significant. 5 against 20 was significant. Cool. Where am I up to? Yeah, and now regardless of the above, perform pairwise Mann-Whitney test. Yes, I've done that now. Mind you, you can actually, let's just change this up. Instead of doing no adjustment method, let's just do pairwise.wilcox.test, and you can actually see the p.adjust.method. If you just look at that, just click through, there are many different ways. You can do a Hochberg, a Hermel, a Bonferroni Hochberg, and FDR. So let's just do FDR instead. FDR, what does that stand for? Franklin Delano Roosevelt, right? So you can still do, you can easily do pairwise Wilcox test with protection, and that simply does that for you, and you can see how one of them is still statistically significant. So you can say one value survived protection or whatever. Some people like to say that. Okay, and now what do I get you to do? Publication worthy plot. Okay, okay, so you just do DF1 summary, DF1, and then the graph I get you to print out looks something like this. So what I've done in this graph is I've done a dot with an error bar, but then overlaid it with jitter plots. Of gray points to try and show some form of distribution of data. So I'd recommend nowadays, I think it's more fashionable to include the raw data alongside plots, but in a bit of a faint way. So that's the code you can use to explore how to do that, and then you can save it using ggSave. Very easy, straightforward. Yeah. Okay, exercise 3.2. So I said, I lied. I actually recruited 40 blogs, and I gave the 40 blogs drug X at the different doses. You randomized the order of the 5 dose administrations according to a balanced Latin square. So, and NB, I'll just tell you now, this data is actually identical to the one we just analyzed when we assumed there were 200 blogs. We just organized it in a different way. And similarly, I also collected the heights and the sex of each blog. So let's read in the data. So df2 equals read.csv. What was the CSV file called? Seminar3 underscore df2 underscore blog. Okay. Seminar3 underscore df2 underscore blog, and then I think it was CSV. So let's do that. So df2 is that. So let's have a look at df2. And then also I want to change df2 ID into a factor variable, dose into a factor variable, sex into a factor, and order also into a factor. And now let's view the df2. You can see we also collected sex, we also collected height, and we also had the order. So blog number 1 received the order 12534 23145, as I've described it with a balanced Latin square design. So now you want to perform a two-way ANOVA on the data. So performing a two-way ANOVA looks like this. Strength is dependent on dose and ID. Because we have 40 people, now we can do that. So, and the ANOVA shows both the dose and ID is statistically significant. So it seems like this drug X, does affect the strength of the individuals, and then also different individuals, i.e., if I use the term ID, the 40 different individuals have different strengths. Is that surprising? No, like people have different strengths, of course. Okay. And now compare this with the two-way ANOVA with the one-way ANOVA. So I'm just going to run both the ANOVAs, and so you can see both ANOVAs over here. Do you see how the dose, because I told you it's identical data, the dose actually gives the exact same sum of squares and exact same mean squares, and yet the dose was not statistically significant in the one-way ANOVA, but the dose was statistically significant in the two-way ANOVA. Now, think about it. In the first one, we had 200N. In the second one, we only had 40N. And yet the 40N seemed to have more statistical power by detecting a difference than the first one. What's going on? And that's the power of having good experimental design. By having good experimental design, you can find out more information about this. And why is this different? Well, you can see how in the second model, the ID model actually detracts away from the residuals. Do you see how in the first model, the residual, the mean square was 414, the denominator was 414.17, but because I introduced this ID variable, it took away 25,966 from 80,000, and so therefore the denominator got even smaller to 54,796 divided by 156 goes to 351.26. My point is that I've introduced an explanatory variable to detract away or take away from the denominator, to explain some of the denominator, right? So the residuals are the unexplained variance. That's what I'm trying to get at. Cool. So yeah, with fewer N, you still can get superior statistical power and through better experimental design. And just notice the numbers of the one-way ANOVA and the two-way ANOVA. And yeah. Okay, what's the next one? Conceptual point. Compare this to we just did that. Now generate a plot-worthy graph, publication-worthy plot of strength versus dose and ID. Okay, so just follow the thing. So yeah, okay. So the graph I plot looks something like this. Yeah, I'm not sure that's publication worthy, but anyway, basically you can see that people's strength modulates with different dose or given. So you can see each line is one individual. So yeah, I mean, some graphs do that. And in fact, I recently published a graph. I recently published a graph that kind of looks like this, where I used straight lines or translucent, not translucent, transparent lines to indicate individuals. I think it's important to have individual data somehow. Anyway, that's how you can publish a graph like that. You can always read through the code and copy it and adapt it for your own use. Now, perform a three-way ANOVA on the data. Strength is dependent on dose, ID, and order. So that's how you do that. That's pretty straightforward. Run an ANOVA. You can find all of them are significant except for order. Order is not significant. Let's go back to the ANOVA. Order is not significant. So now you can say, after accounting for the order effect, the order of giving the drug, we can conclude that there were no significant, we can say the dose was significant or whatever. And so that's a useful thing to say. And then you can also perform an ANCOVA. And if you run an ANCOVA, you'll find sex and height are also significant. I mean, yeah, I guess I'm showing you just the code. That's how you run an ANCOVA. It's actually pretty simple. Now generate a publication-worthy plot of strength against sex and height. So it's just showing you the graph that I drew earlier. How you might have height on the x-axis and strength on the y-axis, and then also, yeah, would there be an interaction effect with sex and height? Yeah, probably, because the lines do intersect. But that's one way in which you could plot an ANCOVA, and yeah, that's the final question. That's the final point of the exercise, just to run you through how to do ANCOVAs and how to run the code for them. And yeah, so yeah, I'll close the session now, but I'll stay around if anyone wants to ask any questions. But thank you for coming in person, and thank you for coming on Zoom. And